Okay, I think, yeah, please start.
Sure. So my name is Yuxiang Peng. I'm from University of Maryland. Today I'm going to talk about two new software tools we developed recently for analog quantum computing. Okay, so motivation. What is analog quantum computing? It may be like kind of weird for us to discuss about analog thing for quantum computing for current development of like how people learn about computing and quantum information. So we start with several problems that is specific to quantum computing, like the factorization, which can be polynomially solved by a quantum computer, and several like quantum simulation problems that you are asked to simulate a quantum system and simulate how it evolves. So in time according to several like Hamiltonians. And this can also be done efficiently by quantum computers. Many theorists have developed quantum algorithms to solve these kind of problems. And the algorithms are always described by like digital quantum circuits in a form like this, where you have several qubits and several wires attached to the qubits. And there are quantum gates as the abstraction for us to describe the operations we want to have the quantum computer to execute. And finally, do some measurements on the qubits. And these measurements can give you some classical results you can read out and extract information from quantum system. So this is how we like theoretically do quantum computing in the form of digital quantum circuits. We always like to we also need to like simplify the overall thinking of how the algorithm design to the level of quantum circuits, and relying on quantum compilers compile the circuits into the actually executed policies for the quantum devices. We see current quantum devices are all analog quantum devices. They are basically very like small quantum systems that can like execute several policies you have engineered for them. Many architectures that is like promising for the development of quantum computing include the architecture of neutral atoms or photons or contacting quantum computers or ion traps. The common thing they share is that their evolution obeys the most fundamental governing equation, the Schrodinger equation, which is described in this small, like very easy to read equation here. This equation basically governs everything about quantum, since basically so basically the difference is about the Hamiltonians executed by each different system. So there's in this paradigm, there's a lot of details hidden in the thing here in the compilers, since you can always you can not always transpile or compile a quantum circuit into an analog policies in a very efficient way. We can open the box here and see that there are many more steps in current workflow of like compilation from circuit to analog devices into basically this still a very simplified paradigm where you can compile quantum circuits into analog policies, which is stored in some like classical form. These policies basically encode a very dedicatedly engineered Hamiltonian, which is basically several system terms and several like controlling terms where our policies UJT here like interact with the system. And we say that analog quantum devices evolve under the description of this Hamiltonian. So it looks still a great thing if we can like simply using this workflow to execute quantum algorithms that can solve quantum problems specific for quantum computers. So what's the difficulty here? Why we still don't see any like real quantum applications in near future for quantum computer? The first very large barrier here is that there's like a very large overhead for algorithm implementation when you transform transform the algorithm to solve the problems into digital circuits. It is still polynomial when we say some algorithm is to solve the problems. There's always a huge constant factor before the complexity of the algorithm, and the constant factor is around at least 100, maybe several thousand, or even several maybe million level, if you count the complexity in the sense of small gates. Besides, there's a high demand of expertise for people that want to program quantum algorithms into quantum circuits. Since programming circuit is itself not very easy way, to do things. Other than, it is even harder for people to learn about how quantum algorithm really works and how to construct all these articles inside the quantum algorithms. So programming the quantum algorithms is also very hard. Another overhead comes from the compiler part, where you translate the quantum gates into analog pulses. To implement the quantum gates, there's still a very large overhead, since you need to pay a large time to evolve the system according to your imagination. And typical data collected from the modern quantum computers is that you can normally do 10 signal gates in a sequence before the system itself is coherent. And the precision of executing signal gates is still very, very bad. For example, the error produced by one signal gate is typically 10 to the -2, that magnitude. So yeah, you cannot do a lot of signal gates, and yeah, things doesn't really works when you try to really compile a large circuit into a quantum for the quantum devices. So we're thinking of making a shortcut for problems like quantum simulation, avoiding the abstraction of digital circuit, where you can directly produce several analog pulses that can be used to solve some quantum simulation problem. And this this detouring can be ignored here. So if we can develop some analog quantum algorithms that directly solves quantum simulation problem and generate some analog pulses, which represents a pretty neat way, very neat way to represent several engineered Hamiltonians, then we can actually exploit the hardware better. And also, this is a natural model for quantum simulation, since if you express a quantum system in a way of the quantum devices, it's very natural to write down all the Hamiltonians and mapping between Hamiltonians. However, the question here is that, do we have the software to do this? Do we have necessary programming languages, compilers, and other type checkers, or wave generators to do the overall thing here? This concept is kind of less developed compared to digital quantum circuits for us to program in analog quantum computing. So there's only very hardware specific tools maybe QuickSkip Pulsar, which can be used to program, QuickSkip Open Pulse, which can be used to program the superconducting computers, and maybe Pascal Pulsar or QEra blockade, they can be used to program the river systems. As you can see that when you want to really implement some algorithms, that analog algorithms that can be executed on quantum machine, you need to spend a lot of time learning the details of the quantum devices, like the river systems and the superconducting systems. And then you have to learn about how to use the programming languages provided by the developers of these hardwares to actually program your algorithm. So we may need a full stack software to support us programming analog quantum computing algorithms or devices. here we present several new languages to like basically tackle this problem. The first, we propose the Hamiltonian modeling language to model the quantum simulation problems. And to describe the different analog quantum devices, we propose analog, abstract analog instruction set as a like new concept, new abstraction we want you to use to work with that expose the very little about the quantum devices, but can be efficient, expressively enough for us to like actually program something. We use an AAIS specification language to actually depict this analog abstraction instruction set. These works are packaged in a like huge framework called SimuQ, which includes all this implementation of these languages and the compilation from the program rewritten in these languages to the actually running pulses for devices. So this is about the first software tool we would like to talk about in a few minutes. The second tool is about differentiable framework for analog quantum computing, which is more or less a analog quantum algorithm, which can lead to applications like optimization and control. This framework directive based on the quantum simulation problem, and it can be seamlessly integrated into SimuQ Framework and help you to do a variational quantum algorithms on the level of like analog level. So we start with the first tool we want to talk about here, which is SimuQ, a domain-specific language for quantum simulation with analog compilation. This is a joint work with Jake Yang, Pengyu Liu, and Xiaodi Wu. So the starting point of SimuQ is about the target Hamiltonian HT we would like to simulate here. As an example, we can write such a Hamiltonian in an expression like this, which is typically treated by the physicists about how they write their Hamiltonians. And you can see that this is like a huge summation with some like time-dependent coefficients and operators like number operator here Ni. And yeah, this is the target we would like to have, and it's the easiest way for like people like physicists to write down what the evolution they would like to have. We then send this target Hamiltonian into SimuQ, and SimuQ can like let you choose what platform you want to compile the things to. For example, if you want to compile it to superconducting systems, you can generate a QuickStream pulse program that can be directly sent to the IBM machine and execute the pulses, can give you the simulation result of this Hamiltonian. You can also ask SimuQ to produce some readable systems result, and it will generate a blockade program, including the position of atoms and the pulses to send to the laser beam, laser tuners. And this program can also be directly sent to the QuCS machine and to simulate the Hamiltonian described here. To be general enough, we can also export some like quantum circuits that's written in OpenQASM and sent to other platforms. We use a like example here about the iron trap machine to illustrate the generality of our framework. The reason here is that basically IonQ didn't provide a pulse level control API, so we use a quantum circuit as an alternative to tackle with their their machines. So the overall idea here is that we want a framework that directly transforms the target Hamiltonian to execute the pulses. So the front end only need to provide the Hamiltonian they would like to simulate in a very easy way, and all the other things can be automatically done by the SimuQ compiler and other transpiler things. And the result is executed pulses that you can directly send to the hardware providers. And this this whole framework is across platform. You can see that you can send to superconductor systems or readable systems or other systems that support pulse level control. So start with the detailed framework of SimuQ. In our imagination, we asked from users to learn about the Hamiltonian modeling language that can be used for them to program their target system in their mind. And we asked the hardware developers to maybe learn about the AAIS specification language and to basically design and program AAIS for their hardware to basically capture the capacity of capability of the hardware. Then we send the target system and AAIS to the Hamiltonian synthesizer to synthesize the schedule that can basically mapping the target system to the hardwares. And it can generate an abstract schedule, and we pass it to the scheduler to generate some concrete schedule where each instruction is like kind of set, the starting time and the ending time of each instruction is like set in the concrete schedule. And we can transpile a concrete schedule into pulse schedule. And the pulse schedule can be directly sent to the common device. So this is the overall framework we would like to discuss in this project. So the first thing to start with is the Hamiltonian modeling language, HML. So in our imagination, we have the booth of a quantum system, or we imagine the quantum system as the booth. It includes several sites. For example, we have some qubit site, Q1, Q2, and maybe a bosonic particle site, which is labeled in the diamond here. For these sites, they correspond to the physical entity in the quantum system. And each site can contain several site operators. Like for a qubit site contains the operator XYZ and default operator I here. For a bosonic site here, it may contain like the annihilation operator or the creation operator. So these are the site operators that belongs to each site. And yeah, the overall idea here is that we use the several layers of new abstractions, like from sites and site operators belonging to each site. And we can then using these site operators to write Hermitian matrices in the form of like algebraic expressions that people usually treat them, how physics usually treat them. And then we can like use the Hermitian matrices to describe evolutions. For example, we want to describe the MIS Hamiltonian, where MIS stands for the maximum independent set Hamiltonian, which is a typical Hamiltonian studied by like people from the River systems like development team. They find this Hamiltonian to encode the classical maximum independent set problems. And the Hamiltonian presented here can be programmed in HML, which has an implementation in Python in this way. So first you declare a system, MIS, and you declare several qubits, which is stored in the list. So these are basically correspond to the qubit size in our imagination, the booth here. Then you can define several operators that you can like call in later programming. For example, the number operator is like described in like I minus z over 2 for each quantum site qi. You can see that all these site operators, the call to all these site operators works like the objective-oriented programming languages, and we design in that way since we want users to like concern less about how the matrix is structured, but all the physics for the quantum system. So you only need to concern about what site you want and what are operators of that site you want to have in your expression. Not about how the matrix is organized in like many other languages like Qtip. Then we basically define the Hamiltonian MIS here in very succinct way of expression. We have like a simple correspondence between all these Hamiltonian terms and all these Python code, where you can see that you can easily write down the summation of all these huge operators in the way of a simple for loop here. And it's very natural for us to understand what this code represents. Lastly, we add the evolution here for a constant Hamiltonian edge evolving for time t, and this can be added to the system. And basically, the MIS now stores all the information about the target system you want to simulate. Another feature here is that continuous time Hamiltonians are hard to compile, so we basically discretize all the continuous time Hamiltonians into a lot of piecewise constant Hamiltonians and basically program in this way. We provide a syntax sugar to automatically discretize continuous time Hamiltonians in our repo if you want to check. So another important concept is about the abstraction of abstract analog instruction sets. The reason behind why we want to have such abstraction other than maybe direct description of machines is that quantum machines are vast different. Different kind of quantum machines different from each other, and you have to learn about how they works one by one, which is very inconvenient for users, like normal users, for you or for hardware developers, for them to basically program the device they would like and having a unified framework for us to do things. This motivates us to provide a unifying description called AAIS, and it can basically expose the necessary information needed for the compiler to tell how to simulate a target system on the device. So we basically abstract the common parts of quantum devices in this way. Physically, you can have signal carriers like wires or maybe some FPGA board that you can use to produce and send signals. And these carriers can carry several delicately engineered signals, like how the signal is transported through the wires. And these signals can carry several effects, like the magnetic field we simply drawn here. This magnetic field can be added together to generate the device effect on the real machine, or to affect the quantum system of the device. So this is basically how we see a general framework for the physical device to be activated, to be affected with engineered pulses. The abstraction we built is based on this framework. So we basically give another name for the steps here. So for carriers, we use signal lines to represent the general purpose of carriers. And signal lines are basically the model for the lines we use, the wires here. The signal lines can carry different instructions which are packaged pulses that can realize several partial Hamiltonians. In these instructions, they can use local variables and global variables to model the configurable parameters of the pulses you can send to the machine. And it has some properties like its native instruction, meaning that it's a direct effect of the pulse, or it's a derived instruction, meaning that the pulse is engineered in a complicated way that you cannot have a very simple superposition property of the instructions. And there's some system instructions, which is basically modeling the system Hamiltonians of the system. Each instruction carries a partial Hamiltonian, which is called the instruction Hamiltonian. That's using the schedule, you can add all these partial Hamiltonians together to generate the total Hamiltonian, which is the Hamiltonian evolving on the real devices. So the schedule here is basically for each signal line, how each instruction is executed on this signal line, for example, line 1 and for time 0 to 10 or maybe 10 to 12, another instruction is coming on the signal line. For each time step, stem, you can have like a summation of the partial Hamiltonian provided by each instruction to construct the total Hamiltonian. So this is how the abstract analog instruction set works. And to program it, we use a language called AAIS specification language. For example, if you want to specify a Rydberg machine, which contains several atoms and several laser beams, we can use like code like in this form. You can see that the infrastructure of AAIS specification machine is very similar to the Hamiltonian machine, where to the Hamiltonian modeling language, where you can define quantum sites and operators in a similar way. We can see that we have like other components of the system and to program here, and they are like decomposed in this table here. So for atom position xi, well, in the Rydberg machine, you can basically configure the position of each atom. It's described by global variables x and stored in the list here xi. Each represents the position of an atom. And the interaction between set I, set j, which is a Vij here, describing the van der Waals interaction between two atoms, whose Hamiltonian is written as C6 over d to the 6 and Nj. It's modeled as a system Hamiltonian since it cannot be turned off and it's always there. And in AAIS specification language, we basically declare an hash and all the summation here about the global variables and the operators, and set it as a system Hamiltonian using the instruction on line 9 here. So for ith laser beam, we create a signal line for it. Basically, the signal line is a carrier of the signal, which is a laser here. For each signal line Li, we declare an instruction delta I to represent the pulse we can send through the laser beam I. The configurable parameters of ith laser beam, including the detuning parameter, amplitude parameter, and the phase parameter, are abstracted as local variables delta, omega, phi of instruction delta I, which is programmed in line 13 here. And they are programmed as local variables, meaning that each instruction call can have different valuation of all these variables. Then we program the effect of this instruction delta I, which is corresponds to the ith laser beam effect, which in Hamiltonian way is described as this long expression. And we simply program this expression into the expression in line 14 here and line 15 here, and to set the instruction Hamiltonian using the method on line 15 here. In this way, we can like basically specify a Rydberg machine which exposes the minimal amount of information we need to use in the compilation about all the laser beams and the atoms, which is in the abstract way, modeling in signal lines and instructions. So next, we want to talk about some details in the Hamiltonian synthesizer, which basically used to generate an abstract schedule from target system and AAIS. So the first step is about finding a set mapping from the target system to the quantum device. For example, if the target system includes like 4 qubit, you want to Q4 here, and the target Hamiltonian include the term like maybe Q1x dot Q2x dot Q3x, and we want to map the system to the quantum device in the like a site mapping describing this join here. We use like a brute force search with heuristic here to basically search for a mapping here. We add some pruning here, is that if Hamiltonian cannot be found on the quantum device under the current mapping, then we break the search here. And in detail, it can be described in this step. So basically, it's like a very brute force search, and we don't have like a clever way to do this site mapping. But using this pruning is generally good enough for us to like run like small system synthesizing for maybe system with like 100 qubits, this search can still be enough for you to use if the target Hamiltonian is like very simple and the target system is clearly very simple as well. After we found such a mapping, which basically map every qubit or site from the target system to the quantum device, we go to the next step about generating the Hamiltonian on the device. So the second step called the coefficient equation building. So we build the equation for each product Hamiltonian P, which is basically storage unit of the Hamiltonians in the SimuQ infrastructure. So basically we built an equation in this form, which is, on the left-hand side is a huge summation among all the instructions specified by the AAIS. And for each instruction, we extract the coefficient of the instruction Hamiltonian of the instruction eta j here, and extract the coefficient of product Hamiltonian P. And we send a valuation of variables into this coefficient, and we use a switch variable to represent whether this instruction is activated in this period of time. And we let the left-hand side to be equal to the right-hand side, which represents the mapped target Hamiltonian to the device according to the side mapping end. And P is still, using the bracket here to represent the coefficient of that term. So concretely, we can see how the coefficient equation looks like for the AAIS Hamiltonian when we want to synthesize it on the Rayburn machine. It basically specifies a huge equation system for each product Hamiltonian, for example, Z1, Z2 here, which you can find some system Hamiltonian term, which for the Z1, Z2 in coefficient C over 4 times x1 minus x2 to the 6, and other terms, then the summation of them should equal to the coefficient in the target Hamiltonian HMS for Z1 and Z2, which is 1 here. To enumerate all the P's that is necessary for the equation, we built a heuristic algorithm to search for all these product Hamiltonians that we want to have in the equation. And we can see that we start with the target Hamiltonian and search for each Hamiltonian term in the AAIS, which can generate several instructions that contains the corresponding terms of this Hamiltonian, and produce the equation here according to all the return instructions. And for the instructions, we can see that some terms appears in the instruction, but not in the target list. And we insert the product Hamiltonian into the list for the further searching. So in this way, we can enumerate all the necessary equations that we want to have to synthesize the Hamiltonian in this compilation process. We then send it to a mixed binary equation system, since the switch variables representing whether an instruction is selected or activated is a binary binary variable. And using the handcrafted solver for the mixed binary equation system, we can solve the equation and get a solution like this. Basically specifies all these variation to these variables, and the variation to the switch variables, and variation to the variables in each instruction call. Obviously, there will be some conflicts in this description, since maybe several instructions on one signal line is like activated at the same time, while we want the signal line only carry one instruction at a time. So we need to solve the conflicting instruction called activated in this solution. We use trivialization as a technique here to basically take with this conflict problem. And we built a conflicting graph for the instructions and find the coloring of it, and use the coloring to do trivialization, and basically write down the schedule in a way that evolve according to the the coloring here. We have the theorem proved about the soundness of our compilation process. We say that if the compilation succeeds, the error can be reduced to arbitrarily small by either increase the decreasation precision or increase the totalization step number or increase the equation solving solver to get like a higher precision solution. We then send the generated schedule, which is a temporal relation between blocks of instruction calls to schedulers and transpilers. Notice that there's like some minor details here that you have to like describe things in the like temporal relations. And we can like use very simple steps like topological sorts and basically first come first serve principle on each signal line for the scheduling process. In this part, we can see that we no longer limit our information from the AAIS, but also how instructions are implemented on the machine. So we can assign the concrete time slot for each instruction call that it will need to actually complete, to effectively produce the Hamiltonian it wants. We use a transpiler to transpile the concrete schedule to pulses using the API provided by the hardware providers. For case studies, we can compile the MIS Hamiltonian, which is a time-dependent one, to systems like readable systems on blockade or IBM machines using like superconducting qubits and also circuit module. You can see that simulation result is very close to the ground truth on the most left-hand side. We can also do pulse-oriented compiler optimization, since you can see that the original implementation of the small instruction provided by QuickSgate is using two-signal gate to synthesize one basically XX rotation. We can make use of the ZX evolution native to the IBM machine to produce small realization of small instruction calls whose pulse duration is proportional to the evolution duration in the schedule. And averagely, it takes like 60% shorter total duration compared to the QuickSgate compiler produced directly from the IBM. And applying this method on the QoA problem, we can have like 22% less losses on real machines executed on the IBM Jakarta. Here we show figures about how the pulses generated by SimuQ is different from the pulses generated by QuickSgate itself. Basically, use like less total duration here. We can also use SimuQ to quickly validate several hypothetical machines about their like total pulse duration. For example, native two-poly evolution are not available for IBM machine for current IBM machine. But if we imagine that it exists, it can also shorten the total duration by a lot. So here's a scalability test we generate for the SimuQ compiler. You can see that most of the tasks can be solved in a reasonable amount of time, in several seconds or maybe several minutes. But for some hard cases, it's still very hard for the compiler to tackle. Like for 40 circuits on in a cycle for the MIS Hamiltonian topology of the topology of the IBM machine is quite complicated, and it takes a lot of time to find the correspondence between sites. Okay, so basically this is about the first tool we want to talk about. I can take a question now if you have, and if no, we proceed to the next tool we want to discuss. Okay, seems no. Then we talk about the differentiable framework we propose for analog quantum computing, which can be used for optimization control. And this is a joint work with Jiaxi Leng and Yilin Chao, Ming Lin, and Xiaodi Wu. So the motivation of this tool is about the success of continuous time system evolution in classical differentiable physics field. where you have a continuous system in this form, written in this form, where you use a set of parameters V to parameterize the continuous times physical system and measure some results and minimize the total loss according to the parameter V here. Then you can generate some gradient feedback from the loss function for you to tune the parameter V here. And in this step, we can basically optimize a problem in on a real machine, on a real physical system. There are several success provided by this framework, like in neural ODE, where the continuous system is basically a neural layer F, describing the ODE, the nature of ODE. And this framework can be applied to reason about the ResNets and several other structures. Another success example is about differentiable physics, where you have F to modeling the physics laws here, and the application can be used to differentiable fluid simulation and traffic simulation. And using this way of optimizing several parameters, you can use it to optimize for real world applications. So the natural question to ask here is, can we substitute the continuous system to quantum system? And the answer, of course, is yes. So basically, we use a quantum system here in the loop here, where the Schrodinger equation is the governing equation that you can use to basically govern the evolution of the system. So for quantum mechanics, the F here is the Schrodinger equation written in this form, and the application can be used to problems like quantum optimization and quantum control. Our proposal is a differentiable framework for the analog quantum computing in this workflow here. So we can make a quick comparison between the circuit models and the analog models. In analog models, you get given some parameters V, we write it into some analog assets corresponding to the pulses, and this can be directly sent to the quantum devices. For the digital quantum computing, the parameter V's are mapped to the variational circuit model, where each component of the vector V is used in the rotation gate. And then we compile this gate into pulse schedules and send to the machine. As we have said before, the compilation step takes a large overhead. So we consider the benefits of using analog assets to program the variational stuff. The benefits here is that we can get better parameterization using analog assets, since it can get rid of the dependence of the parameter and the total duration of the pulse. So we prefer the use of analog quantum computing in the variational frameworks. An overview of our frameworks is like this. For initial state psi 0, we send it to the quantum system, which is controlled by the parameters V1 to Vn. Each correspond to several Hamiltonian terms, and the total Hamiltonian is summation of all these terms. Evolving the system for a time t, the output state is psi t and we can measure it in the form of loss function L. We then calculate the gradient of L to the parameter V in the sampling algorithm to via forward passes, and send the feedback to the parameters to update the system again. And in this way, we can minimize the loss function at the end. The feature of this framework is that the algorithm to calculate the gradient is efficient, robust, and easy to implement. So this framework can be readily applied to real machines in actually current devices. And this can be quite efficient for even near-term machines. So getting into the details here, the system dynamics is described by the Schrodinger equation here, where the Hamiltonian is parameterized by the classical variables V in the form that V parameterizes several analog pulses here, and each analog pulses correspond to a constant Hamiltonian Hj here Hj we require it to be a tensor of polyproduct, a tensor of polymatrices. The loss function here, we use a very generalized way to describe the loss function. Say that for any observable M, we measure the results. And M can encode many things, and basically every information you can extract from the quantum machine. Then the gradient of AL to V is described in this formula. Well, there's a huge integral for time from 0 to t, and the rest of part basically divided into two parts. And you can see it as a chain rule of the gradient of partial derivative of ui to v, and the derivation of L to ui. So the first part is the classical gradient, which is the partial derivative of ui to v. And second part is a quantum gradient, which basically corresponds to the derivation of L to variation of L to uj. So the classical gradient is calculated on a classical computer, and the quantum gradient is estimated by a quantum computer. So this part, we use a chain rule here to basically put the two gradient parts together. We put the algorithm here. So for the quantum part, well, you want to estimate Pj minus Pj plus. You basically use the parameter shift rule here. And you can see that in this submodular, the only difference between evolving the system in the original way is the addition of, it's an insertion of evolving under Hj for a specific duration. Here, Hj is the tensor of polymatrices. And this can typically be done on a quantum machine in a way that you can amplify the terms controlling the Hj term, and all the other terms are so small that they can be ignored. So this can be approximately done. We then express the integral here in the weight of the expectation value and the random process, and model this by a Monte Carlo integration process. Well, you can select a lot of batches here. And for each batch, you draw a random tau here as an estimator and calculate the classical expression here according to the measurement result on the quantum machine. We have a theorem states that the algorithm can produce an unbiased estimation of gradients, and the variance is finite, so the Monte Carlo integration can work good enough for you to estimate the gradients. For the applications, we want to use machine learning techniques to solve analog quantum computing problems, like the ground states and the ground energy search for quantum optimization, and some combinatorial optimization problems. So this using the analog differentiable QuCS framework, it can generalize and outperforms the variational circuit model. For quantum control problems, we can also use this framework to build policies that can perform better compared to the handcrafted policies on the real machines. For problems like state preparation and gate synthesis, since we optimize all these policies on the real machine, it can naturally have the robustness against the inherent machine noises. And all these algorithms are ready for near-term quantum devices. For experiment results of quantum optimization problems, we have like the figure here describe the ground state search for the hydrogen molecule model, and you can see that the bottom two lines here, curves here, represent the R method on same duration of the circuit method. And even even using half of the duration of the circuit model, we can get like better results compared to the one generated the approach provided by basically IBM people using their machine. Compared to other gradient-free method and finite difference method, we get more than 100 times better convergence rate and convergence result in the end. We can also apply this problem to the max cut optimization problem for like for a cycle graph. the figure is missing here, but it's fine. Still, our result is better than circuit ansatz and other different gradient-free methods by a large amount of significant magnitude. So we say that we outperform the other state-of-art algorithms and approaches by orders of magnitude. We can also apply this to control problems like state preparation, like plus state preparation and bell state preparation using the IBM ansatz. And for gate synthesis, it can be decomposed into several states preparation problem. And we use the total loss function as a summation of all these small basis functions, small basis stage preparation. Our method can outperform the typical quantum control algorithm like grape and crab algorithms by like more than 10 times. And compared to gradient-free method, we can also achieve like better results by a large amount. So that's all about this project. And yeah, question is welcome.